Hi all. After we've discussed on the factors affecting the rate of reaction, couple of days on the particle size and also the total surface area of the reactants, today I would like to share with you on the second factor affecting the rate of reaction, which is the concentrations of the reactants. So, how to relate this factor on the effect of concentration of reactants on the rate of reaction? So we know that when we talk about a concentration of reactants, that means the concentration must relate to the concentration of a reactants in solution. Okay, so taking in the concentration equation as a start, where concentration equals to the amount of substance divided by the total volume. So this amount of substance are whatever that contain in a particular volume in a solution. So for this effect of concentration of reactants, we only apply this factor in the reactants, whereby the reactants must be in the solution form. It cannot be in solid and it cannot be gaseous. Okay, so when we say effect of concentration of reactants, a more concentrated reactant solution means more particles per unit volume for reaction. Because according to the concentration equation, concentration equals to amount of substance divided by time. That means if more concentrated a solution is, the amount of substance will be more in a fixed volume. That means more particles per unit volume. To take a very simple illustration, let's say we have two different beakers holding the same solution of 10 centimeter cube. That means the volume of two beakers are the same, and the amount of substance in the first beaker, let's say only 3, but the amount of substance in the second beaker will be 10. Okay, so by calculating the concentration of the two different solutions, this concentration will be the amount divided by volume. 3 divided by 10 equals to 0.3. And the concentration of the second solution will be 10 divided by 10 equals to 1.0. So you can see clearly that the concentration is increasing if the amount of substance in a fixed volume is increasing. So when we say more concentrated a solution or a reactant solution, that means there are more particles per unit volume for the particular reaction. Okay, so if there are more particles per unit volume for a reaction, that means in this particular case, there are more reacting particles per unit volume. So the reacting particles will collide with each other more readily and easily compared to less particles in the solution. So because of this, the rate of reaction will increase. Why is it so? If we explain the effect of concentration in terms of collision theory, we will first start with a more concentrated solution. Means a more concentrated solution means, the first point, more concentrated solution means more reacting particles. In the reaction per unit volume. Because when we set the volume constant, only we can compare the number of particles in the particular volume. So when there are more reacting particles per unit volume, that means point number 2 must be, it will increase the collisions between the particles. Okay, after we increase the collision between the particles, the frequency of collision will increase as well. And because of that, frequency of effective collision will increase, and hence in summary, the rate of reaction will increase. So these are the few flow by using the collision theory to explain the factor related to concentration. When we say we have a more concentrated reactant solution compared to a less concentrated one, that means this more concentrated solution contain more reacting particles. When they have more reacting particles, such as this way comparing to this way, the particles will collide more easily with each other, and hence it increase the collisions between the particles. After we increase the collision between the particles, the frequency of collision will increase, and continue to relate the frequency of collision to frequency of effective collision. That means among the increase of frequency of collision, there are more collisions able to achieve the correct orientation and also the minimum energy requirement, which is the activation energy. Then from there, the rate of reaction will increase. So with this, I hope you understand how to explain the effect of concentration of reactants according to the collision theory. And I would like to share with you on some examples, especially on how to sketch the graph. Okay, look at this particular example question. So usually you will be given with two different sets of reaction condition, and from here, as usual, we have to find out what are the similarities between them. That means the constant reaction condition, and also what are the difference in between the reaction conditions. So according to set 1, we have 1 gram of excess zinc powder reacting with 50 centimeter cube of 0.1 mole per decimeter cube of hydrochloric acid. While for set 2, we also use 1 gram of excess zinc powder reacting with 30 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid. So by looking at the two sets condition, we know that the zinc powder, excess zinc powder, and also the 1 gram, which is the mass of the zinc powder used, are the same. That means the zinc powder will not be the factor affecting the rate of reaction. Okay, so by looking at the second condition, the second reactant, the hydrochloric acid, the conditions are different because the first set is using 50 centimeter cube and 0.1 mole per decimeter cube, while the second set is using 30 centimeter cube and 0.2 mole per decimeter cube. So very obvious, the HCl solution or the hydrochloric acid solution is the one which affects the rate of reaction. So before we continue to analyze on how it affects and how to sketch the graph, first thing first, you have to put down the chemical equation. Chemical equation for this particular example will be the zinc is reacting with HCl to form zinc chloride salt and hydrogen gas. Okay, this is a simple acid reaction between a metal and an acid. So after we put down the chemical equation, make sure you check on the balancing of the left hand side and right hand side, and hence we need to balance it with a 2 on the hydrochloric acid. Okay, and then we continue to fetch the information from the reaction condition into the chemical equation, in which we have 1 gram of zinc, but it is in excess. And for this HCl, two different sets are different. So you can see that the volume used of the hydrochloric acid solution is different, as well as the concentration used is different. So because of that, you have to figure out what are the factors affecting the rate of reaction. Is it on the volume or on the concentration? So if you forgot on the different factors affecting the rate of reaction, we have a total of 5 factors affecting the rate of reaction, in which it is a particle size or the total surface area of solid reactants, the concentration of reactants, the temperature of reaction, the pressure of gaseous system, and the presence of catalyst. So by looking in this condition, we can know that the volume will not be the one to affect the rate of reaction, but the concentration. Okay? So by looking at the changes over here, we know that concentration of reactants, HCl, is the factor that affects the rate of reaction. So now we would like to start sketching the graph, and by looking at the concentration, we know that for set 1 the concentration is 0.1, while for set 2 the concentration is 0.2. And looking at our explanation just now, more concentrated solution will have more particles per unit volume for reaction, and hence according to collision theory, the rate of reaction will increase. So set 2 will be the one with a higher rate of reaction. So now we start to sketch the graph on the release of hydrogen gas per time. Okay, let's say we sketch the first graph in this way, and the second graph we would like to sketch it on the same graph space, but we would like to know whether it will be on top or it will be at the bottom. Okay, so before that, by sketching a graph, one need to know that there are 2 main points. The first one is whether it shows the higher rate of reaction at the initial part of the graph. That means it is whether if it is higher than the original sketch, that means the rate of reaction is higher. If it is lower than original sketch, that means the rate of reaction is lower. And the second important point is whether the tail of the 2 graphs are meeting each other. When we say they are meeting each other, like this, that means the products generation are the same. If let's say the 2 graphs are not meeting each other, that means the product generation are different. One have a higher product generated compared to the second one. Okay, so how to calculate on the product generation? That will need our calculation on the number of moles. If you still remember the number of moles calculation of a solution, I will put down the equation over here. Number of moles equals to mV over 1000. Okay, in which the M is the concentration or the molarity given. The V will be the volume in centimeter cube divided by 1000. So this one is a formula that we need to adopt when we calculate the concentration of a solution, when we calculate the number of moles of a solution given the concentration or the molarity and the volume. So back to this example again. Okay, so we have 2 sets here. So we calculate the set 1. Number of mole of HCl equals to mV over 1000 and equals to 50 multiplied by 0.1 divided by 1000. 50, which is 0.005. While for set 2, the number of moles equals to mV over 1000 equals to 30 multiplied by 0.2 divided by 1000. 0.006. So one can see that for the second set, it has slightly higher number of mole of the HCl solution compared to the first set. The first set gives us 0.005 mole, while the second set gives us 0.006 mole. Then by looking at the chemical equation again, since zinc is in excess and it will not interfere with any of the product formation, so HCl, which is the only limiting reactant, will affect the volume produced of the hydrogen gas. So for first set, if the number of moles of HCl is 0.005 mole, then the volume of the number of mole of hydrogen gas will be 0.005 mole divided by 2. So how should I say, put down here? So for the first set, the hydrogen gas is 1:2. Okay, according to the chemical equation, the hydrogen ratio to the stoichiometry ratio of the hydrogen to the hydrochloric acid is 1:2. That's why for the first set, HCl contains 0.005 mole, in which it will give a hydrogen of 0.005 divided by 2, which is 0.0025. Okay, this is the first set. While for the second set, HCl of the second set gives 0.006 mole. So according to the chemical equation again, and also the ratio between the hydrogen gas to the hydrochloric acid, for the second set, hydrogen gas will be 0.006 divided by 2, 0.003, which is 0.003 mole. So with this, we understand that the second set will generate more volume of hydrogen gas compared to the first set. Okay, so that means the second set will have a higher ending in the graph compared to the first set. And the second set will also have a higher concentration. That means a higher initial rate of reaction. So now we draw the second set. If the second set has a higher initial concentration, make sure the second set has a higher starting of the graph, because it gives a steeper gradient, which means a higher rate of reaction. And from here, it will end slightly higher than here because of the higher number of mole of the hydrogen compared to the first set. Okay, so the second set will have this graph, and the first set will have this graph. So with that, we finish sketching the graph on the first example. So looking at the second example, in order to help students to strengthen your effect of concentration on the reactants, our second example contains two different sets of reaction condition as well, in which the first set contains 1 gram of excess zinc powder, followed by reacting with 50 centimeter cube of 0.1 mole per decimeter cube of HCl, while second set also contains 1 gram of excess zinc powder with 150 centimeter cube of 0.05 mole per decimeter cube of HCl. So some of them we have calculated over here, in which I will not wish to repeat. So look at the two different sets. We know that the zinc powder is still in excess, and it is not the part which affect the rate of reaction. So back to HCl, in which the HCl contain different concentrations. And from the different concentrations, we know that this is the only factor that affects the rate of reaction. So second set contains 0.05 mole per decimeter cube of the hydrochloric acid solution, comparing to 0.10 mole per decimeter cube of hydrochloric acid solution in set 1. So very obvious, the first set with 0.10 mole per decimeter cube is of higher concentration. Hence, set 1 will have a higher rate of reaction. And make sure when we draft the graph, set 1 will have a higher initial rate graph sketch compared to the set 2. Now we go to the second part, which is to calculate the number of moles of the hydrogen gas released in order to understand and justify the ending part of the graph, whether it will combine together or it will separate. So for set 1, so by looking at set 1, we have 50 centimeter cube of 0.1 mole per decimeter cube of hydrochloric acid. So the number of moles will be 0.005 mole of HCl solution. And because of that, according to the equation given again, so I will write down again. The number of moles of hydrogen gas will be half of the number of moles of the HCl. So which is 0.005 here, and we obtain 0.0025 mole. Okay, I'll shift a little bit. And now the second set will give us the number of mole of HCl of 0.0075 mole. Okay, then the number of mole of hydrogen according to the equation will be 0.00375 mole. So, student, please compare yourself on two different number of moles of the hydrogen gas. Which one will give you a higher number of mole? By looking at the two number of moles over here, we know that the number of moles of the hydrogen gas of the second set will be higher compared to the first set. The first set obtained 0.0025 mole, while the second set obtained 0.00375 mole. So that means second set will give a higher volume of hydrogen gas as well in the graph. So let's say we start with one sketch and we do not know which one is it. So let's say this is one graph, okay, of the first set, okay, in which the first set contains 0.0025 mole. So the second set will have higher ending of the graph because of the higher number of mole of the hydrogen, but the second set will contain a lower concentration, which means it will have a lower initial rate. So the graph will be like this. Okay, so you can see that due to the difference in the concentration, we know that 0.1 mole per decimeter cube of HCl in set 1 has higher concentration than set 2, which means the initial rate of the set 1 is higher than compared to set 2. While for the product formation of this particular reaction, the volume of hydrogen gas in set 2 will be higher than the volume of hydrogen gas in set 1 because for set 2, the number of mole of hydrogen gas generated is higher compared to the number of mole of hydrogen gas for set 1. So with these two examples, I hope you understand. And now we have another two examples, and I will go through quickly since you know how to calculate the number of moles, and also you know how to apply the two important analyses on the graph plotting already, which is to remember which one, whether to calculate the number of moles of the product in order to justify on the ending of the graph, and also to find out which is the factor affecting the rate of reaction, and hence to find out which set will have a higher rate of reaction. So looking at equation example number 3 quickly, we also have 1 gram of excess zinc powder in both sets 1 and 2. And for set 1, we have 50 centimeter cube, 0.1 mole per decimeter cube of HCl, comparing to set 2, 25 centimeter cube, 0.15 mole per decimeter cube of HCl. So by looking at the concentration factor over here, set 2 will bear a higher concentration comparing to set 1. So set 2 will have a higher rate of reaction. And also, by looking at the mole of HCl, for set 1, 50 multiplied by 0.1 mV over 1000, this will give you 0.005 mole. So the concentration of hydrogen will be half of 0.005 according to equation, which is 0.0025 mole. While for the second set, the number of mole of HCl will be 0.00375 mole. So we can also calculate the mole of the hydrogen by using the equation. (0.001875 mole. So student, you can now justify which one will give a higher product already. Set 1 gives 0.0025 mole of hydrogen gas, while set 2 gives 0.001875 mole of hydrogen gas. So from here, we know that set 1 gives a higher product, while set 2 gives a higher rate of reaction. Okay, so set 1, we plot the set 1 first. So now we plot set 2. Set 2 has a higher concentration, which means a higher rate of reaction. So make sure we will draw a higher or a steeper gradient with the initial rate over here. And set 2 gives a lower product. So the at the end of the graph, set 2 must be lower than set 1. Okay. This is how we analyze the question and draw the graph. So now we go to the last question. Set 1 still contains exactly the same condition as the previous examples. So we will skip everything, and we know the number of mole of hydrogen is 0.0025 mole. While set 2 will give the number of mole of HCl to be 0.005 mole. So number of mole of hydrogen gas released comparing to the equation will be half of the number of mole of the HCl, in which it will be 0.0025 mole also. Okay, so now student, when you look at the zinc powder, they are still similar in both sets, and for the concentration, they are different. Okay, so look at the concentration of set 1, which is 0.1, and set 2, which is 0.05. We know that set 1 has a higher concentration and hence a higher rate of reaction. While for number of moles of hydrogen gas, for this particular example, two of the hydrogen gas in two sets give the same number of mole, 0.0025 and 0.0025. So for this particular example, the graph will meet at the end. Okay, so when we draw the first one this way, the second graph will be meeting at the end with a lower concentration, which means a lower rate of reaction. So this is set 2. Okay, so with that, we finish sketching the graph for this particular example, in which the same number of moles of the two reaction conditions give us the same product formation, in which the graph combine at the end. And for the different in concentration, the lower concentration of set 2 means a lower rate of reaction, and hence it appears at the bottom of the first graph with a less steep gradient, which means a lower rate of reaction. So with that, with a few examples to share with you, and also on how to explain the effect of concentration in terms of the collision theory, as well as the conceptual understanding on the concentration of a solution. I hope you understand well on how the effect of concentration of reactants affecting the rate of reaction. Thank you.